Good afternoon. My name is Corbin Klatt, and I'm going to present some work that I did with my collaborators, Matt and Young under our research advisors, Sam Coogan and Eric Farone. The work is called Bounding the State Covariance Matrix for Switched Linear Systems with Noise. I'd like to acknowledge NSF support. Let's jump in and look at the system that we will be studying. It's a discrete time switched linear system with noise. There's a additive Gaussian noise term. The system parameters evolve non-deterministically from this finite set of modes. We can also select any set of parameters that belongs to the convex hull of this set right here, and the results will hold. And this is an important system to study because of the time varying nature of it, because of the additive noise. Those types of systems show up in many applications within control theory, and it beckons the need for stability analysis tools. First, let's ignore the noise term and look at a discrete time switched affine system with parameters that evolve non-deterministically from this set. And assuming that our A matrices are all stable, there may be more than one equilibrium point or a different equilibrium point for each subsystem. So if we're switching between different systems with different equilibrium points, it's hard to make assumptions about stability, so we want to classify the infinite time behavior of the switching system with invariant regions of the state space. We're going to do that with a notion of stability called an attractor set. This slide defines it formally, but we'll look at an attractor set as the set of states that the system could end up in at infinite time. And we'll particularly be interested in the minimal attractor, which is the attractor set where no strict subset is also an attractor. And let's look at a depiction of that. So with the system shown at left, there's two sets of parameters, and switching is non-deterministic between the two. So through a large time horizon, a simulation will give us an idea of what the minimal attractor is. And it's that region in blue. And there's each subsystem has an equilibrium point shown by the gold box. We would like to compute the red invariant ellipse that shows us a bound on the attractor set. So what we're going to do in order to get that is follow a procedure that's pretty familiar to nonlinear systems analysis. We're going to formulate a set invariance requirement in terms of quadratic forms. We'll apply the S procedure and then solve a convex program. So the set invariance requirement, we're going to look at an ellipsoid parameterized by a positive definite matrix P, and ellipsoid center XC. And we want to search for an ellipsoid that satisfies the E of X less than or equal to 1, given this statement right here, or such that this statement right here applies, which says in the case over here when an additional time step increases the size of the ellipse, the state should still fit within the one level set of the ellipse for all I. So we're going to take that statement and apply the S procedure, which means that we're going to look for a positive parameter lambda in order to see if there's a feasible P that satisfies this statement. And the lambda in this situation enters in a non-convex manner into this statement. So usually what is done here is a line search over different values of lambda to see which gets us the best P, or the tightest P. So now that we were able to compute an ellipsoid which bounds the attractor set, or bounds the minimal attractor of the switching affine system, we can return back to the system where we add a noise term. And we'll first compute an expression or derive an expression for the covariance matrix of the system state. And that's given by this expression right here, where we have our expected value. And this bar denotes the mean of the state. So noting that the state and noise are not correlated, the expression for the covariance matrix of the system state follows from the definition. When you plug in these values and do a lot of algebra, you end up with an expression for how the covariance matrix of the system evolves in time. And it's this expression right here for x, k plus 1. So we can do some additional manipulation to this equation. And we vectorize x, we vectorize sigma, and we end up, when we perform that operation, and when we also make use of the Kronecker product on the state transition matrix, we end up with this expression in the middle, which shows how the covariance matrix evolves in time as an affine system. And in this case, it's a switching affine system. So since we now have a switching affine system, which we just talked about a moment ago, we can apply the same procedure that we applied earlier in order to bound, this time, the covariance of the system state for the randomly switching system with noise. And here's an example. This original system, given by the A1 and A2 and noise covariance matrices sigma 1 and sigma 2, we augment the system to form the expression on the previous slide for the evolution of the state covariance. And then we apply the bounding algorithm that we discussed earlier. And these graphs show, with the blue dot, a simulation-based approximation of the attractor set for the covariance, for the state covariance matrix. So for a two-dimensional system, there are 3 parameters in the state covariance matrix. And we simulate over a long time horizon how that will evolve. And that's where we get the blue. And then we bound that with, in this case, a very flat ellipsoid. And that is the guarantee of the set of states, or the set of possible state covariances is provided by that ellipsoid. Here's another example of an interesting looking minimal attractor set of the covariances of the system state for this set of switching systems given by these noise covariance matrices. In this case, the covariances form a disconnected set, so it's a very interesting type of set here, and we apply the algorithm and bound the set of state covariance matrices. So in conclusion, we studied the infinite time behavior of a time-varying linear system with additive Gaussian noise, formulating an algorithm to compute a bound on the covariance matrix of the system state. We did that first with a linear affine, by studying a linear affine system, which governs the evolution of the state covariance matrix. And then we bound that by formulating a set variance requirement as a convex program. Thank you for attending the presentation.